Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module multi-vibrators from the paper Electronics. So let us see what we are going to learn in this module. First, we will study transistor as a switch. Second, we will study the two types of multivibrator, that is astable and monostable multivibrator. Lastly, we will study the construction of multivibrator using 555 IC. So students, let us start with a basic introduction about the module. A multivibrator is a relaxation oscillator consisting of two-stage resistance coupled amplifier with the output of each stage being coupled regeneratively to each other. The condition in which the multivibrator stays indefinitely until the circuit is triggered by some external signal is known as a stable state. So multivibrators, they perform variety of useful functions like generation of square waveform, counting, frequency division, generation of time delays, etc. So students, there are three types of multivibrator: astable or free running, monostable, bistable. We will be discussing only two types, that is astable and monostable. Transistor as a switch. Since multivibrators involve transistors which alternate between the conduction and cutoff. So let us consider a transistor in common emitter configuration, and Vi is the step input applied at the base of the transistor. So this shows the IV characteristics of a common emitter transistor, which shows which explains all the three regions, that is saturation region, active region and cutoff region. In saturation region, transistor is fully on, and at cutoff it is fully off. So let us now discuss the conditions in which the transistor is act as an open switch and the conditions in which it act as the closed switch. Now let us first discuss the open switch. When Vi is 0 as shown in this figure, it implies IB equal to 0. So transistor is in cutoff region and no current flows through RL except the leakage current ICEO, and the switch is in off position as shown in this figure. So in this condition, the VCE is maximum, which is equal to VCC, and since there is negligible drop across RL when IC is approximately equal to 0. Let us now consider the closed switch case. So here consider Vi, which is applied to turn on the switch by applying the base current, that is IB. This will cause the transistor to switch on quickly and drive the transistor into saturation, VCE is approximately equal to 0, and the ground at emitter has now effectively been transferred to collector so that full VCC voltage has been placed across RL. Switching time in a transistor. So this waveform shows that due to a capacitive effect in transistor, application of square wave input to the base emitter junction is not followed directly by the change in output voltage. So as you can see from this figure, TR is the rise time, the time required for the output to change from 10% of its initial value to 90% of its final value. TD is the delay time, that is the time taken by IC to start rising. So the turn on time will be T on will be the summation of TD and TR. When VBE goes to 0, there is a delay before IC starts to change due to the charge stored in the transistor being cleaned out, and this is called as charge storage time, TS. Now here TR is the fall time, that is the time required to reach the 10% of its initial value. So the turn off time will be the summation of TS plus TF. Let us now discuss the first kind of multivibrator, the astable multivibrator. The astable circuit has no stable state. So with no external signal applied, the transistors alternately switch from cutoff to saturation at a frequency determined by the RC time constants of the coupling circuits. So here, astable multivibrator circuit consists of two cross-coupled RC amplifiers as shown in this figure. Here RL1 and RL2 are the collector resistances for transistors T1 and T2 respectively. C1 and C2 are the coupling capacitors. R1 and R2 provides the on-state base current to the two transistors respectively during saturation region. Let us now discuss the working of this circuit. Now, when the power is applied, one of the transistor conducts more than the other due to circuit imbalance as shown in this figure. Now let us consider that transistor T1 is conducting and T2 is off. Thus, the output VC1 of the transistor T1 is approximately 0 volts and VC2 is 12 volts. Hence, the capacitor C2 gets a path to charge up, which is shown by this arrow in the figure, through RL2, and base emitter junction of transistor T1 is approximately 12 volts. So here the capacitor C1, which was previously charged up to 12 volts, that is when T2 was conducting through RL1, but when T1 conducts, a path is provided for C1 to discharge through T1 and R1. So in this figure, it shows the discharging path for C1 through R1 and T1. It also shows how a negative voltage is coupled to the base of T2. The initial pulse of discharge current from C1 through R1 makes the base of T2 suddenly very negative, that is approximately minus 12 volts. This causes the T2 to be cut off as assumed. So students, T1 is kept in the conducting state by base current provided from VCC through R2. So VB1 is slightly positive. The charging current of C2 through RL2 has now ceased. So the length of time for which T2 is held off is determined by the time constants of discharging of C1 through T1 and R1. Now these shows the other two cases, that is the first figure shows that this allows C1 to be charged very quickly, which is through RL1, and T2 causing the increase in the positive voltage at the base of T2 and aiding the turning on of the T2 transistor. Now next, this figure shows that at the same time C2 is also allowed to discharge through T2 and C2, that is coupling a large negative voltage at the base of T1. So this turns T1 off quickly and the collector voltage VC1 rises towards plus 12 volts. However, the voltage at the collector of T1 is somewhat less than 12 volts at this instant due to the voltage drop across RL1 occurring while C1 is recharging. So this is relatively short time, but it causes a rounding of the rising edge in VC1. So these are the waveforms which is explaining the turning on of one transistor T2 and its falling voltage at the collector, which permits the discharging of a capacitor which drives the transistor T1 into cutoff. So the rising voltage at the T1's collector feeds back to the base of T2, tending it to turn it on. So the students, the waveform can be explained as when T1 is in saturation, the whole VCC drops across RL1 and VC1 equal to 0, and hence the lower end of RL1 is at 0. T2 is cut off, so no voltage across RL2, and hence the lower end of RL2 is at a potential VCC. When lower end of RL1 is at 0 potential, C1 starts charging through R1 towards VCC. So when the voltage across C1 rises more than 0.7 volts, T2 is forward biased and starts conducting. T2 is soon driven into the saturation. So when T2 is in saturation, Vc2 becomes almost zero. That is the potential of lower end of RL2 decreases from Vcc to 0. This potential decrease is applied to the base of T1 through C1 or C2, and consequently T2 is driven to cutoff. So in the cutoff position of T1, the lower end of RL2 is at zero potential, and hence C2 starts discharging through RL2 to potential Vcc. When voltage across C2 is more than 0.7 volts, T1 is forward biased and starts conducting. So students, let us now discuss the different circuit conditions. That is, first, when T1 is in saturation region, that is Vc1 at T equal to 0 is equal to Vce saturation equal to 0, or we can say IC1 saturation equal to Vcc minus Vce saturation by RL1. Now here VB1 on is greater than equal to VBE on equal to VBE saturation. So IB1 on equal to VBB minus VBE saturation divided by R2. So second case is when T2 is in off region. That is Vc2 off equal to Vcc, IC2 at T equal to 0 equal to 0, IB2 off is approximately equal to minus Vcc plus VB2 on. So the frequency of oscillations, that is during the discharge of C2, your VB2 will be equal to Vcc minus IC1 R1. The initial discharge value of current IC1 is IC1 equal to Vcc plus Vcc by R1. That is, capacitor charges up to Vcc approximately. The current decays exponentially with a time constant R1 C1 because VB2 equal to Vcc minus 2 Vcc exponential minus T by R1 C1. Now suppose VB2 equal to 0, then 0 equal to Vcc multiplied by 1 minus 2 exponential minus T by R1 C1, implying exponential of T by R1 C1 equal to 2, since Vcc is not equal to 0, or T equal to R1 C1 log 2 equal to 0.694 R1 C1. Thus, the off time T2 for transistor capital T2 or the on time of transistor T1 is given by 0.694 R1 C1. Similarly, off time T1 for the transistor T1 or on time of T2 is T1 equal to 0.694 R2 C2. So total time period will be T equal to T1 plus T2 equal to 0.694 R1C1 plus R2C2. If R1 equal to R2 equal to R and C1 equal to C2 equal to C, then capital T will be 1.39 RC. So the frequency of astable multivibrator is F equal to 1 by T equal to 0.7 divided by RC. So minimum value of beta HFE, that is beta 1, equal to R2 by R12 and beta 2 equal to R1 by RL2. That is RL1 equal to RL2 equal to RL and R1 equal to R2 equal to R. So when beta equal to R by RL and then IC will be IC1 will be R1 will be equal to IC2 R2. So this implies R1 will be equal to IC2 RL2 divided by IC2. So IC2 by IL2 is equal to beta equal to HFE. R1 is less than equal to HFE RL2. So HFE will be greater than equal to R by R1. So the proof is that to ensure the oscillations, the transistor must saturate so that R1 and R2 must be chosen. With the HIE, the DC current gain of the transistor, let us assume that T2 is saturated so that its collector to emitter voltage is approximately equal to the base to emitter voltage. Then the voltage drop across R1 must be equal to the voltage drop across RL2. Thus transistor will be saturated if. Let us now discuss another kind of multivibrator whose circuit is shown over here. Now here the difference is that this multivibrator circuit is having a one stable state. Now here a signal trigger is applied to the base B2 of transistor T2 and a regenerative action takes place which drives the transistor T2 to completely cut off. So the voltage at Y2, the output, rises approximately to VCC. Now T1 comes in conduction. So the device may be driven into saturation or it may operate within its active region. In either case, the current I1 exists in RL1 which causes a voltage drop I1 RL1 at Y1 and thereby decreasing the voltage at B2 by the same amount because voltage across the capacitor C cannot change instantaneously. So here the multivibrator is now in quasi-stable state and the circuit will remain in this state only for a finite time because B2 is connected to VCC through R. Now B2 will again rise in voltage when the voltage at B2 is equal to the cut-in voltage of T2. A regenerative action takes place. This turns the transistor T1 off and eventually returning the multivibrator to its initial state. Now here the triggering signal is applied at t equal to 0 and reverse transition occurs at t equal to capital T. Construction of multi-vibrator using 555 timer circuit or the IC. Now the 555 timer IC, the figure and the pinout diagram is shown over here, and this was first introduced around 1971 by Signetics Corporation as SE555 NE555 and was called as the IC time machine. It provided the circuit designers with a relatively cheap, stable, user-friendly integrated circuit for timer and multi-vibrator operations. Now the inside view of this 555 timer is also shown over here, and the operation, the detailed operation is as follows. The functional block diagram shows that the device consists of two comparators, three resistors, and a flip-flop. A comparator is an op-amp that compares the input voltage and indicates whether the input is higher or lower than a reference voltage by swinging into saturation in both the direction. The operation of the 555 timer revolves around three resistors that forms a voltage divider across the power supply to develop the reference voltage, and the two comparators connected to this voltage divider. The IC is quiescent so long as the trigger input, that is pin 2, which remains at plus VCC, and the threshold input pin 6 is at ground. Assume the reset pin 4 is also at plus VCC and therefore inactive, and that the controlled input voltage pin 5 is unconnected. So the three resistors in the voltage divider have the same value, that is 5K in the bipolar version of this IC, and hence the name 555. So the trigger and the threshold comparator, the reference voltages are 1 by 3 and 2 by 3 of the supply voltage respectively. So here the control voltage input at pin 5 can directly affect this relationship, although most of the time this pin is unused. So the internal flip-flop changes the state when the trigger input at pin 2 is pulled down below plus VCC by 3. When this occurs, the output pin 3 changes the state to plus VCC and discharges the transistor pin 7 is turned off. So the IC, the trigger input, can now return to plus VCC. It will not affect the state of IC. However, if the threshold input pin 6 is now raised above plus 2 by 3 VCC, the output will return to ground and the discharge transistor will be turned on again. When the threshold input returns to ground, the IC will remain in this state, which was the original state and which was the original state when we started this analysis. So the easiest way to allow the threshold voltage to gradually rise to plus 2 by 3 VCC is to connect it externally to a capacitor being allowed to charge through a resistor. In this way, we can adjust the R and C values for almost any time interval we want. So the 555 can operate in either mono, bistable or astable mode depending on the connections and the arrangement of the external components. Thus, it can either produce a single pulse when triggered or it can produce a continuous pulse train as long as it remains powered. So students, let us summarize what we have learned in this module. First, the detailed explanation of transistor as a switch. Second, working of astable multivibrator along with the switching time and all the waveforms. Third, monostable multivibrator. Lastly, the construction of multivibrator using 555 IC was discussed. Thank you.